10 gigabit Ethernet is a group of computer networking technologies for transmitting Ethernet frames at a rate of 10 gigabits per second. It was first defined by the IEEE 802.3e 2002 standard. Unlike previous Ethernet standards, 10 gigabit Ethernet defines only full duplex point-to-point links which are generally connected by network switches. Shared medium CSMA CD operation has not been carried over from the previous generation's Ethernet standards. Half-duplex operation and hubs do not exist in 10 GBE. Like previous versions of Ethernet, 10 GBE can use either copper or fiber cabling. However, because of its higher bandwidth requirements, higher-grade copper cables are required, Category 6A or Class F Category 7 cables for links up to 100 m. The 10 gigabit Ethernet standard encompasses a number of different physical layer standards. A networking device may have different PHY types through pluggable PHY modules, such as those based on SFP+. At the time that the 10 gigabit Ethernet standard was developed, interest in 10 GBE as a wide area network transport led to the introduction of a WAN PHY for 10 GBE. The WAN PHY encapsulates Ethernet packets in SONET OC-192c frames and operates at a slightly slower data rate than the local area network PHY. The adoption of 10 gigabit Ethernet has been more gradual than previous revisions of Ethernet. In 2007, 1 million 10 GBE ports were shipped, in 2009 2 million ports were shipped, and in 2010 over 3 million ports were shipped, with an estimated 9 million ports in 2011. As of 2012, the price per port of 10 gigabit Ethernet relative to its 1 gigabit counterpart still hindered more widespread adoption, even though the price per gigabit of bandwidth enabled by 10 gigabit Ethernet was already about one-third compared to the bandwidth cost of its 1 gigabit predecessor. Standards. Over the years the Institute of Electrical and Electronics Engineers 802.3 Working Group has published several standards relating to 10 GBE. These included 802.3e 2002, 802.3 ARC 2004, 802.3 and 2006, 802.3 April 2007 and 802.3 AC 2006. The 802.3e 2002 and 802.3 ARC 2004 amendments were consolidated into the IEEE 802.3-2005 standard. IEEE 802.3-2005 and the other amendments were consolidated into IEEE STD 802.3-2008. Physical layer modules. To implement different 10 GBE physical layer standards, many interfaces consist of a standard socket into which different PHY modules may be plugged. Physical layer modules are not specified in an official standards body but by multi-source agreements that can be negotiated more quickly. Relevant MSAs for 10 GBE include XMPAC, XFP and SFP+. When choosing a PHY module, a designer considers cost, reach, media type, power consumption, and size. A single point-to-point link can have different MSA pluggable formats on either end as long as the 10 GBE optical or copper port type inside the pluggable is identical. XMPAC was the first MSA for 10 GE and had the largest form factor. X2 and XPAK were later competing standards with smaller form factors. X2 and XPAK have not been as successful in the market as XMPAC. XFP came after X2 and XPAK and it is also smaller. The newest module standard is the Enhanced Small Form Factor Pluggable Transceiver, generally called SFP+. Based on the Small Form Factor Pluggable Transceiver and developed by the ANSIT 11 Fiber Channel Group, it is smaller still and lower power than XFP. SFP+ has become the most popular socket on 10 GE systems. SFP+ modules do only optical to electrical conversion, no clock and data recovery, putting a higher burden on the host's channel equalization. SFP+ modules share a common physical form factor with legacy SFP modules, allowing higher port density than XFP in the reuse of existing designs for 24 or 48 ports in a 19 inches rack width blade. Optical modules are connected to a host by either an XAUI, XFI or SFI interface. XMPAC, X2, and XPAK modules use XAUI to connect to their hosts. XAUI uses a 4-lane data channel and is specified in IEEE 802.3 Clause 48. XFP modules use a XFI interface and SFP Plus modules use an SFI interface. XFI and SFI use a single-lane data channel and the 64B/66B encoding specified in IEEE 802.3 Clause 49. SFP Plus modules can further be grouped into two types of host interfaces, linear or limiting. Limiting modules are preferred except when using old fiber infrastructure which requires the use of the linear interface provided by 10 GB ASELRM modules. Optical fiber. There are two classifications for optical fiber, single mode and multi-mode. In SMF, light follows a single path through the fiber, while in MMF it takes multiple paths, resulting in differential mode delay. SMF is used for long-distance communication and MMF is used for distances of less than 300 m. SMF is a narrower core which requires a more precise termination and connection method. MMF has a wider core. The advantage of MMF is that it can be driven by a low-cost vertical cavity surface emitting laser for short distances, and multi-mode connectors are cheaper and easier to terminate reliably in the field. The advantage of SMF is that it can work over longer distances. In the 802.3 standard, reference is made to FDDI-grade MMF fiber. This is a 62.5 AA micrometer core and a minimum modal bandwidth of 160 MHz by kilometer at 850 nm. It was originally installed in the early 1990s for FDDI and 100 base FX networks. The 802.3 standard also references ISO IEC 11801, which specifies optical MMF fiber types OM1, OM2, OM3 and OM4. OM1 has a 62.5 AA micrometer core while the others have a 50 AA micrometer core. At 850 nm the minimum modal bandwidth of OM1 is 200 MHz by kilometer, of OM2 500 MHz by kilometer, of OM3 2000 MHz by kilometer and of OM4 4700 MHz by kilometer. FDDI-grade cable is now obsolete and new structured cabling installations use either OM3 or OM4 cabling. OM3 cable can carry 10 GB 300 meters using low-cost 10 GB ASESR optics. To distinguish SMF from MMF cables, SMF cables are usually yellow, while MMF cables are orange or aqua. However, in fiber optics there is no uniform color for any specific optical speed or technology, with the exception being angular physical connector, it being an agreed color of green. There are also active optical cables. These have the optical electronics already connected, eliminating the connectors between the cable and the optical module. You plug into standard optical module sockets. They are lower cost than other optical solutions because the manufacturer can match the electronics to the required length and type of cable. 10 GB ASESR. 10 GB ASESR is a port type for multi-mode fiber and uses 850 nm lasers. Its physical coding sublayer 64B/66B PCS is defined in IEEE 802.3 Clause 49 and its physical medium-dependent PMD in Clause 52. It delivers serialized data at a line rate of 10.3125 Gbits. Over obsolete FDDI grade 62.5 micrometers multimode fiber cabling, it has a maximum range of 26 meters. Over 62.5 micrometers OM1 it has a range of 33 meters. Over 50 micrometers OM2 a range of 82 meters. Over OM3 300 meters and over OM4 400 meters. OM3 and OM4 are the preferred choices for structured optical cabling within buildings. MMF has the advantage over SMF of having lower cost connectors because of its wider core. The 10 GB ASESR transmitter is implemented with a VCSEL, which is low cost and low power. OM3 and OM4 optical cabling is sometimes described as laser optimized because they have been designed to work with VCSELs. 10 GB ASESR delivers the lowest cost, lowest power and smallest form factor optical modules. For 2011, 10 GB ASES is projected to make up a quarter of the total 10 GB adapter ports shipped. There is a non-standard lower cost, lower power variant sometimes referred to as 10 GB ASES-RL. This is interoperable with 10 GB ASES but only has a reach of 100 meters. 10 GB ASELR. 10 GB ASELR is a port type for single-mode fiber and uses 30 and 10 nm lasers. Its physical coding sublayer 64B/66B PCS is defined in IEEE 802.3 Clause 49 and its physical medium-dependent PMD in Clause 52. It delivers serialized data at a line rate of 10.3125 Gbits. 10 GB ASELR has a specified reach of 10 km, but 10 GB ASELR optical modules can often manage distances of up to 25 km with no data loss. The 10 GB ASELR transmitter is implemented with a FBA copyright ROT or distributed feedback laser. DFB lasers are more expensive than VCSELs but their high power and longer wavelength allow efficient coupling into the small core of single-mode fiber over greater distances. 10 GB ASELRM. 10 GB ASELRM, originally specified in IEEE 802.3 AC, is a port type for multimode fiber and uses 30 and 10 nm lasers. Its physical coding sublayer 64B/66B PCS is defined in IEEE 802.3 Clause 49 and its physical medium-dependent PMD in Clause 68. It delivers serialized data at a line rate of 10.3125 Gbits. 10 GB ASELRM allows distances up to 220 meters on FDDI-grade multimode fiber and the same 220 m maximum reach on OM1, OM2 and OM3 fiber types. 10 GB ASELRM reach is not quite as far as the older 10 GB ASELX4 standard. To ensure that specifications are met over FDDI grade, OM1 and OM2 fibers, the transmitter should be coupled through a mode conditioning patch cord. No mode conditioning patch cord is required for applications over OM3 or OM4. Some 10 GB ASELRM transceivers also allow distances up to 300 meters on standard single-mode fiber, however this is not part of the IEEE or MSA specification. 10 GB ASELRM uses electronic dispersion compensation for receiver equalization. 10 GB ASER. 10 GB ASER is a port type for single-mode fiber and uses 1550 nm lasers. Its physical coding sublayer 64B/66B PCS is defined in IEEE 802.3 Clause 49 and its physical medium-dependent PMD in Clause 52. It delivers serialized data at a line rate of 10.3125 Gbits. The 10 GB ASER transmitter is implemented with an externally modulated laser. 10 GB ASER has a reach of 40 km over engineered links and 30 km over standard links. 10 GB ASEZR. Several manufacturers have introduced 80 km range pluggable interfaces under the name 10 GB ASEZR. This 80 km PHY is not specified within the IEEE 802.3 standard and manufacturers have created their own specifications based upon the 80 km PHY described in the OC-192/STM64SDHSONET specifications. The 802.3 standard will not be amended to cover the ZR PHY. 10 GB ASELX4. 10 GB ASELX4 is a port type for multimode fiber and single-mode fiber. It uses 4 separate laser sources operating at 3.125 Gbits and coarse WDM with 4 unique wavelengths around 30 and 10 nm. Its physical coding sublayer 8B10B PCS is defined in IEEE 802.3 Clause 48 and its physical medium-dependent PMD in Clause 53. It allows a range of 300 meters over FDDI grade, OM1, OM2 and OM3 multimode cabling. 10 GB ASELX4 also allows a range of 10 km over SMF. For MMF links the WDM output needs to be coupled through a SMF offset launch mode conditioning patch cord. This is explained in subclauses 53.6 and 38.11.4 of the IEEE 802.3 spec. Until 2005 October, GBASELX4 optical modules were cheaper than 10 GBASELR optical modules. 10 GBASELX4 was used by people who wanted to use both MMF and SMF with a single optical module. 10 GBASELX4 is now an obsolete technology and has no significant market presence. 10 GBASEPR 10 GBASEPR originally specified in IEEE 802.3 ARV as a 10G Ethernet PHY for passive optical networks and uses 1577 ANM lasers in the downstream direction and 1270 ANM lasers in the upstream direction. Its physical medium-dependent PMD is specified in Clause 75. Downstream it delivers serialized data at a line rate of 10.3125 Gbits in a point-to-multipoint configuration. 10 GBASEPR has three power budgets specified as 10 GBASEPR 10, 10 GBASEPR 20 and 10 GBASEPR 30. Copper, 10G Ethernet can also run over twin-axial cabling, twisted pair cabling, and backplanes. 10 GBASECX4 10 GBASECX4AA Euro was the first 10G copper standard published by 802.3. It uses the XAUI 4-lane PCS and copper cabling similar to that used by InfiniBand technology. It is specified to work up to a distance of 15 am. Each lane carries 3.125 G board of signaling bandwidth. 10 GBASECX4 offers the advantages of low power, low cost and low latency, but has a bigger form factor and more bulky cables than the newest single-lane SFP Plus standard and a much shorter reach than fiber or 10 GBASET. This cable is fairly rigid and considerably more costly than Category 5 or 6 UTP. Shipments of 10 GBASECX4 today are very low. Although some network vendors offer CX4 interfaces which can be used for either 10G-base Ethernet or for stacking of switches at higher speeds. An example of combi stacking Ethernet are Dell Power Connect PCT6200, PCT7000 and the 1G Power Connect blade switches PCM6220 and PCM6348, SFP plus Direct Attach, also known as Direct Attach, 10G SFP plus CU, 10 GBASECR, 10 GBASECX1, SFP+, or 10 GBEQ SFP cables. Direct Attach uses a passive twin-ax cable assembly and connects directly into an SFP+ housing. SFP+ Direct Attach has a fixed-length cable, typically 1 to 7 am or up to 15 am in length, and, like 10 GBASECX4, is low power, low cost and low latency with the added advantages of using less bulky cables and of having the small form factor of SFP+. SFP+ Direct Attach today is tremendously popular, with more ports installed than 10 GBASESR. Backplane Ethernet Euro, also known by its task force name 802.3 APA Euro, is used in backplane applications such as blade servers and modular routers switches with upgradable line cards. 802.3 APA implementations are required to operate in an environment comprising up to 1 meter of copper printed circuit board with 2 connectors. The standard defines 2 port types for 10 Gbits and a 1 Gbits port type. It also defines an optional layer for FEC, a backplane auto-negotiation protocol and link training for 10 GBASEKR where the receiver can set a 3-tap transmit equalizer. The auto-negotiation protocol selects between 1000 base KX, 10 GBASEKX4, 10 GBASEKR or 40 GBASEKR for operation. 40 GBASEKR4 is defined in 802.3 bar. New backplane designs use 10 GBASEKR rather than 10 GBASEKX4. 10 GBASEKX4, this operates over 4 backplane lanes and uses the same physical layer coding as 10 GBASECX4. 10 GBASEKR, This operates over a single backplane lane and uses the same physical layer coding as 10GbASELRSR. 10GbASET, 10GbASET, or IEEE 802.3 and 2006, is a standard released in 2006 to provide 10 Gbit connections over unshielded or shielded twisted pair cables, over distances up to 100 meters. Category 6A is required to reach the full distance of 100 meters and Category 6 may reach a distance of 55 meters depending on the quality of installation, determined only after retesting to 500 MHz. 10 GbASET cable infrastructure can also be used for 1000 base T, allowing a gradual upgrade from 1000 base T using auto negotiation to select which speed to use. 10 GbASET has latency in the range 2 to 4 microseconds compared to 1 to 12 microseconds on 1000 base T. As of 2010, 10 GbASET silicon is available from several manufacturers with claimed power dissipation of 3/4W at structure widths of 40 nm, and with 28 nm in development, power will continue to decline. 10 GbASET uses the IEC 60603-78P8C connectors already widely used with Ethernet. Transmission characteristics are now specified to 500 MHz. To reach this frequency, Category 6A or better balanced twisted pair cables specified in ISO IEC 11801 Amendment 2 or ANSI-TIA 568C2 are needed to carry 10 GbASET up to distances of 100 m. Category 6 cables can carry 10 GbASET for shorter distances when qualified according to the guidelines in ISO Trail 24750 or TIA 155A. The 802.3 and standard specifies the wire level modulation for 10 GbASET to be Tomlinson-Hiroshima pre-coded pulse amplitude modulation with 16 discrete levels, encoded in a two-dimensional checkerboard pattern known as DSQ-128. Prior to pre-coding, forward error correction coding is performed using a low-density parity check code, with the parity check matrix construction based on a generalized Reader-Solomon code over GF26. By contrast, PAM5 is the modulation technique used in 1000 base T gigabit Ethernet. WAN PHY, the WAN PHY uses the same 10 Gbases, 10 Gbasel and 10 Gbasee optical PMDs as the LAN PHYs and is designated as 10 Gbasesw. 10 Gbaselw or 10 Gbaseew. Its physical coding sublayer 64B/66B PCS is defined in IEEE 802.3 Clause 49 and its physical medium-dependent PMDs in Clauses 52. It also uses a WAN interface sublayer defined in Clause 50 which adds extra encapsulation to format the frame data to be compatible with SONET Street's 192c. The WAN PHY was designed to interoperate with OC-192/STM64 SDHSONET equipment using a lightweight SDHSONET frame running at 9.953 Gbits. The WAN PHY can drive maximum link distances up to 80 km depending on the fiber standard employed. 10 GBE NICs, 10 GBE network interface cards are available from several manufacturers. These plug into ordinary computer servers using PCI Express and provide one or more PHY module, LC or 8P8C connectors. See also: Notes and references. External links, full text of the IEEE 802.3 standard, IEEE 802.3 Ethernet Working Group, Ethernet Alliance website, University of New Hampshire Interoperability Laboratory 10 Gigabit Ethernet Consortium, First Global Independent Comparative Third-Party UTP-STP Study, Description of SFP plus Direct Attach Server NIC in Top-of-Rack Concept.